Hi, this is Ethan Pickett, and this is Soup Lab 5. Introduction. This lab makes use of a magnet slowing down in a tube made of a conductor to explain Faraday's law. According to Faraday's law, when the magnet falls through a tube of a conductor, the magnet creates an induced current. According to Lenz's law, the magnetic field from an induced current opposes change in flux. For this reason, the magnet falls through the conducting tube at a much slower rate than just air. Next, we have the procedure. Measure the dimensions of the aluminum foil tube. Mine are shown below. Drop the magnet through the tube, recording it with your smartphone. Repeat this procedure 4 more times. Find the timestamps of when the magnet enters the tube and then leaves the tube. The difference between these times is what we are experimenting for. Mine are shown on the table on the next slide. Here are my results. I got an average of 1.074 seconds that the magnet was in the tube. Here are some important equations that I will use in my computational model. Shown are the equations for the current, the flux in the tube, the magnetic force on a ring being a section of the tube, and then the net magnetic field, which we use superposition to calculate because the rings add together. The magnetic force of the rings add together due to the law of superposition. Shown here is my computational model. As you can see, the slope of the velocity versus time graph plateaus while the magnet is inside the tube. This shows that the net force during this period of time is 0. My time in the tube is 0.9 seconds. Here's my code. Here is the dipole equation to calculate the magnetic field of the dipole. Here is the flux calculator that calculates the flux due to the conducting tube. Then it runs it through this loop and then uses superposition. Here's the ring current. Here's the current of the ring found by flux, which is equal to the EMF over the resistance. Using superposition, we can find that the magnitude of the force on the magnet is equal to the previous force on the magnet plus the magnitude of the force on a ring. And then we can find the net force by just adding the magnetic force to gravity. Here are some key assumptions that were made. Firstly, we assumed that the magnet can be treated as a dipole mathematically, when in actuality, we would need to account for the shape of the magnet to get a truly accurate model. We also assume that the conducting tube in the program is identical to the one used in the experiment, even though this is impossible. Interpretation. The red color responds to the clockwise view, and the blue responds to the counterclockwise view. If the current induced is negative, then it flows in the clockwise view, and positive for the counterclockwise view. If you flip the magnet around, the magnitude of the force is the same. However, the induced currents are flipped around. The computational time in tube is slightly less than the experimental for reasons previously mentioned. It could be made more accurate if it didn't assume the magnet as a dipole. Because the velocity versus time graph plateaus while the magnet is in the tube, the change in velocity is 0, and we can assume that the net force is 0. This means that the force of the induced current and the Earth's gravity are equal while the magnet is in the tube. Conclusions. My computational result and experimental result differed substantially, with each being 0.919 and 1.075 seconds respectively. This could be due to experimental factors such as the imperfectly wrapped aluminum foil or my hand moving In reality, the computational model is less accurate than the experimental model, as the computational model makes several critical assumptions. If the resistivity of the conductor is close to zero, then the current will be high, resulting in a high decrease in the velocity through the tube. If the resistivity was zero, then the magnet would levitate. If holes were cut in the tube, the geometry of the tube would be incomplete. Therefore, the induced dipole is made weaker and thus less magnetic field, thus less force slowing the magnet down.